Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School, and welcome to today's lesson on randomness, probability, and simulations. This is the beginning of Chapter 5 of our textbook. I want to begin by first defining a sample space. A sample space is, in a random process, is a set of all possible non-overlapping outcomes, and we typically denote it as a capital S. So, what is the sample space of rolling a six-sided die? Well, what are all possible outcomes? I could get a 1, 2, 3, 4, 5, or 6, and I've denoted it a sample space with the letter S. What is the sample space of tossing two coins? Well, I could get two heads. The first coin could be a head and the second tail. Two tails, the first could be a tail and the last could be a heads. Now, I want to define event. An event is any subset of the sample space, and events are usually designated with uppercase letters. So the probability of A, and that's how I denote it, that's the probability of a specific event A occurring. Now, there are two interpretations of probability. This first one is the classical or theoretical interpretation. In this interpretation, all outcomes have equal probability. If there are n events, the probability of any particular event is 1 out of n, such as flipping a coin or rolling a die. That is the classical or theoretical interpretation. In most instances, it assumes that all outcomes are equally likely. The other interpretation of probability is the experimental or long-run relative frequency interpretation. In this interpretation, the probability is estimated based on the history or experiment, such as the probability of making a free throw is based on the history of shots made. So to find out probability, we have to look at history or some kind of an experiment. Between these two types of interpretation, the AP examiners definitely prefer the latter approach. We are in an era where the experimental or long-run relative frequency interpretation is winning the day. According to the classical interpretation, if all outcomes in a sample space are equally likely, the probability that an event E will occur is determined by this formula. So to find our probability, we count the number of outcomes in E and divide that by the total number of possible outcomes in S. So if I were to ask you, what is the probability that a randomly chosen student at CHS is a senior? And if I told you that there were 3,000 students and each class had 1,000, you would say the answer would be 1,000 out of 3,000 or 1 out of 3. Now, let's turn to the equally likely case, because that's the case associated with the classical approach. If we roll a fair die one time, what is the probability of getting an even number? Well, to do this, we have to calculate our sample space. Then we have to calculate the event A, that is choosing and getting an even number. And my possible successes in A would be 2, 4, and 6. I count those, I get 3. I take 3 divided by 6, that's the number in the sample space, and I get 0.5. I know this seems kind of obvious, and I'm making a difficult job out of something really simple, but the language of this area is a little bit cumbersome, so bear with me. Now, let's turn to the other approach. What is the probability using the long-run relative frequency interpretation? Here, probability describes what happens in the long run. Behavior that is unpredictable in the short run may have a regular and predictable pattern in the long run. This is definitely the approach that the AP examiners like to see. I give you this problem first of all. Let's say I flip a coin, and I'm going to say I'm going to count the number of heads and divide that by the total number of trials. So on my first flip, I get a head, so the proportion of heads becomes 1. The second flip is a tail, so now I've got 1 head and 1 tail, so I'm at exactly 0.5 proportion of heads. The third one is another tail, so I drop down to 33% heads, and then you can see it bounces all over the place. How do we interpret this? When asked to interpret probability using this approach, we say when we toss a coin many times, the proportion of heads is approximately 0.5 in the long run. When you're asked to do this, make sure you include the word approximately and in the long run, because that signals to the exam reader that you are using the experimental or long run approach. I'm going to take a second here and do this process a little bit here. I have a spreadsheet here, and in this spreadsheet, if I buzz over here, you can see I have a random number generator that is generating numbers between 0 and 5. I tell it if the number is less than 0.5, then I'm going to call it a tail, and otherwise it's going to be a head. So then I count the number of tosses, the number of times I get a head, and then this becomes the proportion of heads. So I'm going to slide over here so that you can see the probability in action. So if I refresh my numbers, you can see that this time I started out, I got a few heads in a row, but in the long run, the proportion heads towards 0.5. It becomes really apparent if I look at not just over 50 trials, but instead look at over 200 trials or even 1,000 trials. So let me just randomize all my numbers, and again, the proportion of heads gets very close to 0.5. I'll try it again, 0.5, 0.5. So in the long run, we can't predict what the coin will do next toss. It might be heads or it might be a tails, but in the long run, it will approach 0.5. That is the long run frequency approach. Let me come back to my slides here. Okay. The law of large numbers. First of all, let me say this. A random process generates results that are determined by chance. So in order for it to be considered a random process, we have to have some chance. The law of large numbers says that the more times we repeat a random process, the sample statistic, maybe the sample mean or the sample proportion, will approach the population parameter, that is the true population mean or the true population parameter. So in our case, we repeated the flipping of a coin 1,000 times, and as we did so, our sample proportion p hat approached the true population parameter 0.5. Random phenomenon is not predictable in the short run, but does have a pattern over the long run. Now, the law of large numbers is important because it guarantees, and I use that word in quotes, it guarantees stable long-term results for the averages as long as a large number of observations is considered. Let me just speak briefly about two industries that do rely on the law of large numbers. One is casinos. Casinos rely on the fact that the results over many trials is predictable. They structure their payoffs or odds slightly in their favor so that the money paid out to players who win is just a little bit more, or is just a little bit less than the money that they take from those who on average don't win. So on average, if you go to a casino in Las Vegas, you will find that on average, you can't predict what you're going to do on a single game, but on average, the games are structured so that the casino will tend to win in the long run. Otherwise, they wouldn't be out there building these big casino buildings. Another industry that relies on this is the insurance industry. They rely on the law of large numbers. Back to this, what is probability? I want to examine some myths about probability. Suppose I toss a coin 6 times and I get 6 tails. Is the next toss more likely to be a head to make up for the imbalance? No. The law of averages is a myth. We still can't predict what the next coin will be. There is no such thing as the law of averages. Is the next toss more likely to be a tail? Well, if we've got all those tails, are we more likely to have the next one being a tail? No. Coins have no memories. memory might sound like a unusual word in this case, but actually memory is a statistical term. A lot of chance processes do have memories. So for example, you're driving a car and you haven't had a breakdown in the first 1,000 miles, you haven't had a breakdown in the next 1,000 miles, but say when you're up to 60,000, maybe 100,000 miles, then what has happened in the past does start to affect what will happen next. So there are many chance processes that do have memories, but tossing a coin is not one of them. I give a definition of memoryless for those who are interested. Randomness. A phenomenon is random if individual outcomes are uncertain. I give you this example. The proportion of randomly selected men aged 20 to 24 years old who die any one year is about 0.0015. We don't know who that might be, but if you insure enough young men of that age, you're going to be you will then know about how much you're going to have to pay out in the form of insurance proceeds. So the insurance company can therefore set its premiums to cover its payouts and its overhead and hopefully some profit. Now, the next part of this unit of this first class is about simulations. We've done a few simulations in this class before. I call your attention back to the hiring discrimination activity and the smelling Parkinson's activity that we did earlier this year. Those were simulations. We had you do some simulations on Desmos. When you are asked to describe a simulation, let's say that we give you a difficult statistical problem and you can't solve it paper and pencil. So you think, well, let me try and answer this question by setting up a simulation. In fact, this is a decent proposal. If you're stuck on an AP exam question and you just don't know how to solve a problem, go ahead and describe a simulation that would solve that problem. And I think you'll get a sympathetic audience and probably some good partial credit. So what are the steps to describing a simulation? First of all, you have to ask a question of interest about the chance process. So we give you the problem, you're going to state it in a form of a question. Then you have to come up with a plan. I want you to describe how to use a chance device to imitate one repetition of the process you're trying to solve for. For example, I want you to state the digits that will represent the different outcomes. Okay? And then tell me what you will record at the end of each repetition. The next step of describing a simulation is to perform many repetitions. So you have to demonstrate how you would do it. And lastly, you are asked to conclude the results of your simulation to answer the question of interest. And I'm going to switch screens here for a second and show you how this looks in a real world problem. So here we have, this is a problem on your guided notes for today. We have suppose a basketball player announces that a certain player is streaky. What does that mean? That is, announcer believes that if a player makes a shot, then he's more likely to make the next shot. Okay, so what he's saying is that the outcomes are not independent. If you're streaky, the outcomes are not independent. Your success last time increases your probability of making the next shot. As evidence, he points to a recent game where a player took 30 shots and had a streak of 7 shots in a row. Is this convincing evidence of streakiness, or could it have occurred simply by chance? Assuming this player makes 70% of his or her shots and the results of the shots do not depend on previous shots, how likely is it for the player to have a streak of 7 or more shots? Okay, so first thing is we ask a question of interest. So I put this in the form of a question. What is the probability that a player makes 7 or more shots in a row when they're given 30 shots and the player is a 70% shooter? That's how I phrase the question. What is the probability of making 7 or more shots in a row when you're given 30 shots and you have a 70% shooting percentage? Now the next step, I have to describe a random process that imitates my problem. Okay? I'm going to use a random generator on my calculator to generate random integers between 0 and 9. In the calculator function, you would just write it like that: ran integer # 0 and 9. And on your calculator, that will generate random number integers between 0 and 9. Now I have to assign certain outcomes. Well, this is a 70% shooter, so I'm going to say 0 through 6 are shots that are made, and 7 through 9 are shots that are missed. So I have 7 out of 10 shots that are being made, and 3 out of 10 being missed, because I start at 0, remember. So I want to perform a trial of 30 shots, and afterwards I'm going to record the length of the streaks and note the longest streak in 30 shots. So that's a description of my plan. Then I have to do it. I have to actually, write out, do it once, So I listed out some random digits that my calculator spit out. And I'm looking for streaks of shots where the streaks of made shots. What's a made shot? Those are the numbers 0 through 6. So this first yellow highlighted box, those are all made shots in a row. I made 1, 2, 3, 4, 5, 6, 7, 8 shots in a row. Then I missed one. Then I made 5 shots in a row. Then I missed one. Then I made 2. I made 2. But I have to do this 30 times for one trial. And when I'm done, I just make a note of the longest streak. Okay? And so then I have to come to a conclusion. I have to do this 30 times and then repeat that process. So I have to come to a conclusion. Well, let's say that this is what I did. Here's my outcome, a dot plot with my tests. I did this 50 simulations. I did 50 simulations of 30 shots. Okay. Well, you can see in many of the games, my longest streak was 6 shots in a row. I had some going out to 12, 13, but there weren't many out there in the 14 and 15 range. Okay, and none more than 16, more than 15. So I write this: the graph below shows the longest streak in each of 50 simulations. Based on these results, it is plausible that a 70% shooter got a streak of 7. Because remember, our basketball player got a streak of 7. The announcer was impressed that he got a streak of 7. Based on these results, it is plausible that a 70% shooter got a streak of 7 in a row by random chance alone without being streaky. So we're going to say that getting 7 in a row is not evidence of streakiness. And that's my conclusion. So in this assignment set today, you're going to be doing some of these simulations, and I hope you use this technique. That's today's lesson. Thank you very much.